the proof of this uniform boundedness theorem. Therefore, I thought that maybe I will do another video on the proof, giving some more explanations, especially looking at one of the examples, which would give some insight into the steps that we use in the theorem. So let us briefly recall the theorem. X and Y are, X is a Banach space, Y is a normal linear space. It's a normal linear space. So let lambda alpha belong to A be a collection of bounded linear transformations on not the entire one, but a subcollection of that. Okay, where A is an index. A is an index. Then two things can happen. One is either the collection is uniformly bounded by some M. So this is the uniform boundedness for alpha belonging to, or supremum of is infinity. Supremum of norm of lambda alpha x for alpha belonging to A, that is the supremum taken over alpha belonging to A, is infinite. For every x belonging to a G delta set, which is dense in. So that is the statement of the theorem. So there are two possibilities, either this or this. Okay. So this is the collection could be either uniformly bounded, or if not, what you can say is that the supremum of lambda alpha, norm of lambda alpha x for over supremum taken over alpha belonging A, for each x this is happening, it would be infinity for each x belonging to a G delta set, which is dense in X. So these are the two possibilities that can happen. So we will now give the proof of this. We will discuss the proof of this theorem. Now, before that, I will set two examples. Let me designate it as example 1. Example 1 is the following. A you take as interval 0 to infinity. That is the index set. And we define lambda alpha from R2 to R2. R2 to R2. So you are taking x equal to R2 define it as equal to psi alpha x for alpha beta. Where is a function from A to R, and we assume that which is bounded on A, that is less than m or what we are assuming is possibly something like this. This is your A, this is A, and if you plot this, so this is the function would be something like this. And you can take it as something like this, but we take a non-negative function. So if you take a non-negative function, something. So this could be psi alpha. Okay. Now this is a bounded function. Bound is something. This is it. So this is alpha. This side. So this is the, and you see that this is a bounded function. The bound is given by, this is the scenario then. Okay. When you see that is equal to log x. So each lambda alpha is bounded. Okay. Now, what we do this, that is supremum of that is the definition of that, and this is of course less than 1. So in this case, lambda is uniformly, in this case, so we take example 2. Example 2. Example 2, we take again A to B. Yeah. Then we take psi alpha in this case to be alpha. So we define again a linear transform, right? Right. Now you see that this is alpha belongs to here. This is of course unbounded. Okay. This takes the place of psi alpha. In this case, the psi alpha is unbounded. Okay. Right. So this is the other scenario. So in this case, what happens is you have psi alpha unbounded. Now you can see that this is equal to so supremum alpha A which is equal to 0. This is equal to which is equal to infinity. And that is true for every x. This is true for so these are the two examples that we look at, and that corresponds to the second scenario that is given in the theorem. Okay, now let us go to the proof of this theorem. This is where I rush through for want of time, and later on I thought that possibly nice to revisit the proof. So what this says is the following. The geometry of the problem. Okay, let us see that You take the unit ball in X. Then lambda alpha maps B10 into a ball of radius M. This is what you are saying. You are saying this, that is norm of is less than or equal to, this is the norm in Y, this is less than or equal to so if this is less than 1, then this is less than or equal to. So this gets mapped into a ball of radius. Right. So that is the geometric interpretation of the first part of the theorem. Second part of the theorem says that there exists an x belonging to x. So this is the first part of the theorem. The second part of the theorem says on a dense uh, G delta subset of x, lambda alpha x is not confined. is not confined to any bounded or any bounded ball in Y. So this is the interpretation of the theorem. So that gives the geometry of the theorem. Okay, that there exists no bounded ball in which this is confined to or x belonging to a given. Then it's a subset. So let us now prove this theorem. We set phi x to supremum of x belonging to A x. Now this is for every x belonging to okay. So you are taking the norm of lambda alpha x for each x belonging to x and taking the supremum of that. This becomes a function of alpha and taking the supremum of that over alpha. So this is what you define as phi. So this is the function. Now we define, okay, let us see what this is. In example 1, what is this? Norm of alpha x equal to of x and you have this is the supremum of and you know that psi alpha is a bounded function on A, therefore this is of course no, this is what okay right. The other one, it is unbounded because you are taking psi alpha to be alpha and A to be the unbounded set. Right. Now we define the set of all x for which so this is your phi x and this is the set Vn. Now Vn would be what in this case? In this case, you see that phi x is greater than n. That means supremum of which is bounded by m is greater than this is what you take is the set What is this one? This is equal to m times norm of x, and that is greater than n, or norm x greater than. This is the set. So this is what you have. In our case of R2, this is the complement of the closed unit circle with radius n by. So not unit circle. This is n by. This is the set that you get as Vn. So this is. So Vn is the complement of the closed unit circle with radius n by. So now we make some observations. So we claim open. Each Vn is open. Or we have, now we know that lambda alpha is a bounded linear operator, therefore is continuous. And you see that norm function on y is a continuous function on y is a continuous function, a continuous real value. Therefore, is a composition of two continuous functions, and hence continuous. Therefore, now you take phi x so phi x, which is equal to supremum of alpha belonging to A of is hence a lower semi-continuous function because we are taking the supremum over alpha belonging to A. That's why the lower semiconductor, and that is what is needed for our work. As far as we are concerned, we don't forgot to put the date on top. That so this is 25. And hence each Vn is, so that completes the proof of the openness of it. So that is done. Now we look at the possibility. If one of these sets Vn fails to be dense in X. So just look at what happens in the first example that we have looked at, because what you have is the lambda alpha. We have explored the example, and in that example we have phi x is kilometers. Where m is equal to supremum of alpha belonging to. This is what you have, and this is assumed to be finite. In first case, this is finite. Okay. Therefore, you see that the corresponding Vn is going to be greater than n, which is equal to n by m. Okay. So this is the situation that you have, and you have see something else. This is it. Therefore, you see that this is not dense in this is not dense in This is not dense in what you have. Okay, so that's what we get in the first case. Therefore, consequently, you can see in this example, there is some x naught you can find here, and some such that a ball of radius r is completely contained in this region. Okay. Consequently, what you have is there exists x naught belonging to x are positive such that norm x less than r implies okay. So you can find if some are such that this entire ball is lying in this particular in the complement of A. Okay, so you have this x naught plus x is not belonging to Vn. X naught also does not belong to Vn. Therefore, we can write this. Therefore, for all x, we can write lambda alpha x therefore what you have is this phi of x naught is less than or equal to n, and phi of therefore what you have for every x such that r, the r we have chosen here, we have norm of lambda alpha. So see, what you can do is you can write x as x plus x naught minus x naught. Okay, that's what you can write, and therefore you get this less than, sorry, this is x naught. Therefore this is less than what you have n plus, which is equal. Now choose m to be equal to 2n by r. Okay, then bounded by. Okay. So this is what you get. This is so you get norm. Now mod norm x less than r. So this implies so you get like this. So you take r 1 by r r. Now that is r. Now you see you can take the supremum over this because we are working in that in this ball. Okay. Therefore, that is going to be bounded by 2n by r. Okay. So that's how it comes, right? So norm of lambda alpha is less than pi. So this is where so that norm x norm y so that's the sort of analysis that you do, and therefore you choose m equal to. Okay. So that is the so that completes the first part. Okay. So the crucial step is this. One is this one. The other one is assuming that you have assuming that this is Vn Vn fails to be dense in X. So the crucial steps are we assumed Bn that is the crucial assumption that comes. So we have to look at the other possibility. So we consider now possibility that is there exists no n every Vn is dense in. This is the assumption. Now Vn is open. For every n. Therefore, you see that intersection Vn is a G delta and each Vn is therefore this intersection is also because each Vn is density and you are taking the intersection over n of this is a G delta set. Now by Bayes' theorem, each and is dense this is where Bayes' theorem comes to take. Okay. Thus for every x intersection Vn we have equal to infinity. What is phi x equal to infinity? That is equal to infinity. So this is the second part of the statement. and that actually completes the proof of the theorem. Okay, I think that completes our work on that, and I have very hastily done this part. That is, I thought that I would repeat it again. Okay, thank you very much. Okay, let me also make a remark. How does this work on the example? So if you look at the example, in example 2, where we have assumed that alpha x. Here you see that Vn equal to what? This is equal to all of R2 probably the singleton, and Vn is density. And therefore you are taking the intersection of all this, and therefore you get the result. Okay, right? And therefore for each x, so each x not equal to 0, you are going to get this what is that, supremum of lambda alpha x over alpha belonging to A equal to 0. That's the result. So I think I'll conclude that.